Hello guys, we're going to be going over these topics briefly. Let's see if I still understand them or if I can explain them good. So we're going to go first about scaling. There's vertical scaling and horizontal scaling. So what is scaling? Scaling is kind of saying, scaling is saying as a system grows, is it still maintainable? So as we add, growing is kind of like as we add like new features, is it still maintainable? Right? So that's what it is. So in this example, there's vertical and horizontal scaling. Let's say you run a service. So software as a service. It's also known as SaaS, which is known as software as service, as a service. That's why it says SaaS. That's what it stands for. Software as a service. SaaS for short. So basically, you run a service which has to run on a server. So basically, a server could be anything. It could be like a computer. So this is a server. Actually, let me write it smaller. So this is a server. So this is a client. This is client. So basically, a client talks to a server, and then that server sends information back. So talks to, or actually just kind of say requests. So request information from the server, and this is the server. I'm gonna just label it. And the server kind of sends back information, sends info. And that's your service, right? Well, we're talking about scaling now. So this is basically just the regular architecture. This right here is, this is SaaS. This is software as a service. So what happens is sometimes is that you'll have many, as your amount of clients grow, right? Because in this example, we have one client. Let's say there's many clients. They're asking for many requests. The server could be overloaded, right? So how can we prevent the server from being overloaded so that each client gets really good service instead of it being laggy or not working properly? Well, the first one is called vertical scaling. Okay, so this is going to be your server. Let's call this as basic. So to vertically scale it, we could do, there's two options for scaling. There's vertical and horizontal. Let's say this one's vertical, right? So it's kind of just making your server stronger. We could add stuff like more RAM, which is more access, random access memory. We could add more RAM. What else? Oops. We could add more RAM. We could add more cores. Right? And that costs a lot of money, right? So cost a lot. And there's the other one, which is horizontal. Okay, so that one would be instead of using one basic server and just upgrading into a better one, we could just have a bunch of smaller basic servers, right? Um, the one that's preferred more often it would be vertical or actually horizontal, a mixture of vertical and horizontal scaling, but mostly horizontal. Just because, let's say, if the system is overloaded for vertical scaling, you only have one system, right? So it would fail and your whole service would be down. Versus if you had one server fail for horizontal, that you would still have three more as backup. The service might be a bit slower, but at least there's something to work with, right? And that's what horizontal scaling is referring to. Now, load balancing. So I would say we covered that. Let's go to load balancing. Let's go ahead and write over here. So a load balancing, let's see. Right, so load balancing basically just uses, so as the client talks, this is, I'm just going to say client requests, right? Let's just say they request something. They request your service. So when they request a service, we go back to this example right here, where they go ahead and request a service from your server. Instead of going directly to the server, it actually just goes to something called like a load balancer. I'll write it like this. This is gonna be that load balancer. Right, and this load balancer runs algorithms such as it could be like first in, first out. Um, but hold on, let me write the architecture first. So this will be using horizontal scaling. So instead of the client talking directly to our servers, the client will actually just talk to the load balancer, and the load balancer will distribute those requests. Okay, and the load balancer actually uses different algorithms. So the question might be, how does a load balancer know which request to send to which server? Well, it uses different algorithms. The algorithms it uses could be first in, first out. So that's one. One could be round robin. Another one could be shortest job first. I think first in, first out is usually not used. Actually, no, it usually is used. Last in, first out is not used. Yeah, at least for load balancing, it's not. So these are like the three main algorithms that they use. There's many more, but those are the ones worth knowing. So this could be like server 1, 2, 3, 4, 5. Yeah, this just prevents it from being overloaded, right? Because how would we know that this client is trying to talk? Let's say if they all send to 5, then 5 would fail just because it has too much. That's why we use load balancers. Let's see what else they have. I would say we did load balancing algorithms, pretty good. Auto scaling. Oops. Auto scaling groups. Okay, so what is auto scaling? Remember what I mentioned when we do horizontal scaling? Something like this. This is going to be horizontal scaling. Well, um, sometimes we don't actually, if we have access to 5 servers, we don't actually want to keep them all at the same time. Um, so we're going over, let's see, auto scaling. Okay. So basically what auto scaling is let's say we have 5 servers. Oops. Let's say we got 5 servers. If As long as these servers are running, it costs money. It costs money to keep them running. So what do we do instead? We have auto scaling. So basically, let's say peak hours would be probably like when people are working like 9 to 5 a.m. 9 to 5 when they work at 9 a.m. p.m. When they work these hours, these servers are being used the most. Say most used hours. So at that time, we would want 5 servers to run. We could just say 5 servers up. Well, at other hours, let's say past 12 a.m. 12 a.m. to like, let's say, like 6 a.m., right? There's less traffic. So with that in mind, why would we run 5 servers, right? Why would we run all 5 servers when it costs money to keep them running? When we could just run maybe two. We could just run 2 servers, right? And just exclude these when it comes to this time frame at 12 to 6. Should run only 2 servers to keep costs down. Keeps cost low, right? That's basically what auto scaling is. We kind of just define an algorithm or kind of just have it scale automatically based on the time that we set for the auto scaling group. And this will help save money, and that's why we do auto scaling. Okay, so now we have AWS Lambda and serverless. Oops. Serverless and AWS Lambda. Well, AWS Lambda is actually a service. So this is just kind of a web service. And the web service is a serverless, which it doesn't literally mean serverless. It just means that the client doesn't have to worry about actually scaling the groups. So for example, if we just have code, we have some code that we just want to run on a server, right? Before we would have to do like an EC2, which is like an instance, which is okay. So this is like a server. So we would have to put the code in the EC2 and then run to get our results. So let me write this better. So we'd code, and then we'd go to EC2, and then kind of just run it there, and then return results. Yeah, right. This is the whole entire. This is before. This is what we did before. Old way. Right? We'd have to do a bunch of steps. You see these steps? Right? With serverless. Let's see. With serverless. Oops. With serverless, we could actually just skip that. All right, but it skips it in the client's view. In reality, it still runs all of this, but to the client, they don't have to worry about any of that. So client could just code, give it to like AWS Lambda, and then instead of having to set it back, instead of having to just run all of this, like set up an EC2 and do all of this stuff right here, AWS Lambda, it just runs code directly. So that the client doesn't have to worry about setting up their servers or setting up anything. They just write, all they have to do is just worry about code. So that's the advantage. Has to code only. No worry. Not have to, where'd my pen go? Yeah, they don't have to worry about, oh shit. I say not worry about server setup. Right, so that's really helpful. And event driven architecture, so EDA. Okay. Tight coupling. I think these play hand to hand, and this is kind of like the storage is okay. Let's go EDA. Let's go ahead and explain EDA. Event-driven architecture. So basically, before we would have to do, so let's say we have, this is our service, and just if we have an online service, let's say this is our service, right? So we'd have to send a request out to our client. Actually, let's say it's gonna be the client, there's something else. So we before we would have to do send this out to a client to say if we're trying to buy something, right? Here, let me start. Okay, so this is a client. They're trying to buy something from your website, and then before they buy something, they put in that request, and then you have to put in another request to just say like a third party, saying that is this payment real? Real. It's kind of like a verification, right? And then afterwards, you have to wait for this response, and then you get one back. They would say something like real, right? Then you would have to send another request back to like, let's say your warehouse. Then they would say, okay, can ship. We could ship it. Yes, right? Then after that, we could go ahead and just charge them, charge the money. So this is back to the client, charge. Right? You see how this is synchronous? So this runs in synchronous. So basically, let's go ahead and go back. Okay. So event one, so it'd be like this. So we walk this. The client. Okay, so this is our service. It's the client. So the client asks our service. Our service verifies if the payment is real. Then it waits for that request. Oh, if it's real, okay. So we get that information back. Then we have to go to the warehouse and say, hey, can you even ship this? And then they go back to us and they say, okay, yeah, they can ship it. And now we have to go ahead and charge the client. You see how this is like, let's say, 1, 2, 3, 4. It's just a bunch of steps, right? Steps. Takes time. And this is what tight coupling is. Tight coupling. Well, to fix this, we actually have another setup right here. Let's go ahead and write that EDA, which is event-driven architecture. So this is your service. We could go ahead and have all the requests. So what was that? What was the problem again? We had to do verification, client requests. Another one would be let's say warehouse. Right, so instead of having that, we have all the requests go into a letter. So we'll say something like a letter, information, info letter, kind of like an email or something, right? So we get this, we package it, we package all those requests, right? See all of these requests. We pack them up, and then we send them, and we put inside the letter. Then we have each service, such as the warehouse, the client, the verification service. We just send them all out at the same time. Right, so let's see, we send them all at the same time. At the same time. Right, so instead of having to do all of this, we could just do them all at the same time, so it runs asynchronously. Well, you might have a question, right? Let's say the service did not fail. It did fail, so the payment was fake, right? But all of these said it was okay. What we would do is actually have a rollback. So it would send information back to the main receiver, the person that with the mail. Then this mail would send information back here, and it would cancel all of these. So yeah. So all of these would have to be true before actually setting the request and shipping out the item. Otherwise, yeah, if something did go wrong, we'd message the main receiver. Let's see, what was the word? These are called the subscribers. And I think these are called maybe like the influencers. So, see, these are influencers. And they're subscribers. So, so the influencer would be this. Then they would sell like mail. Let's say that's mail, and the mail goes to all the subscribers. There's many subscribers. Yeah, and then if all the subscribers are checked, I want to make sure we're on the same page. If they're all checked, or if something fails, then they go ahead and message the influencer. The influencer sends mail, and subscribers could get the new update. And that's basically what event-driven architecture is. So yeah, we just package all the events that need to be happening in this mail, and we go ahead and send it out to whoever's subscribing. That's what EDA is. And that helps reduce tight coupling because we don't want tight coupling. That's not good. It's a lot of dependencies. Now I think that this is like the type of SNS. I think they're kind of like storages, I think. I want to say that. I'm not actually too sure. Container orchestration. ECS and EKS. I think containers, okay, I could go over containers. So basically every single person has their own computer. So containers. So everyone has their own computer, and each computer is kind of unique, right? My computer isn't like your computer. So to ship a product, we go ahead and just get all the features of your computer. We box them up into a container. So when we ship our product, we ship our software, they already know what to expect, or what their computer needs to download to be like your computer. So that's what containers are. So let's say we bottle them up, and let's just say this is like a service. Service. So we have your container in here. I'm gonna say C, and this is a service. So when someone gets this package right here and they could run it, they have everything they need to start using your program. Versus if we did not have containers, then let's say they try to run your service. It could run if their computer was similar to yours, but most of the time it's not accurate. And we're chasing 100% accuracy or something close to that. That's why you use containers. Okay, now databases. Well, there's a bunch of databases like MongoDB. I'm gonna skip over that though. Availability and availability zones, durability, infrastructure as code, cloud formation. I think I went over enough today. Go ahead and end the video here. But yeah, these things are pretty simple at the end. I guess I could go over one of them. I'll think maybe infrastructure as a code could be kind of confusing, so I'm gonna go explain that, I guess. So infrastructure as code. Infrastructure as code. So what is this, right? Well, in a database, we have let's say database. If we want to update something, it'll have much stuff like, let's say, update, erase, um, read. All right, it'll have a bunch of this. So if you wanted to update something, you would go ahead and just go to this form, fill it out, and then it'll just update automatically, or not update. Yeah, it'll update. Right. Well, infrastructure as a code actually fixes this because the issue was be like if you updated something wrong, then it would just ruin the whole database. Well, with using infrastructure as a code, if you wanted to update something, we could just write something like a script. So if I wanted to run an update, run update. Instead of going through this, I'm gonna just call it a GUI. This GUI, graphical user interface. I would just write it as code. So I'd write code, and then that would actually just update the database. And you're wondering, why would I want to write code to update the database versus just having this? Because I don't have to code it if I do it this way. Well, code is actually better just because you could do one is code review, which is super important, especially when updating like a large database with information, just so that information doesn't get corrupted. Number two is code is actually easier to read. Yeah, but the top reason is probably code review, just because before you update something, you would want to do a review, and code really helps with that. It's easier to read, it's more understandable. Okay, availability zones is making sure that your service is available in different zones. Durability is like, let's say natural fires or something. You have like another database, so that when that database is destroyed, you have another one. It kind of plays into horizontal scaling. So let's say if this one was destroyed, you would have another one up. Cloud formation, um, cloud development kit, Terraform. I think these are all part of making your service accessible. Well, okay. Well, that's the end of the video. I went over all of this, which is just kind of just going over cloud architecture. Or you could also just say cloud computing. Okay. See you guys later. Thank you for watching. Hopefully you guys learned something new today.